Good morning. This is Hope Reactor. Now, let's begin today's news.
Japan found a way to remove just one plastic from mixed waste. Mixed plastic is one of recycling's hardest problems. A bottle, a food tray, a piece of clothing, and a foam cushion may all look like plastic, but chemically they are completely different materials. Once those materials are blended, glued, woven, or molded together, separating them can become so difficult and expensive that they are simply burned or discarded. Now, a Japanese research team has developed a different approach. Instead of separating every material first, they use chemistry to target one specific plastic polyurethane. They do not destroy everything. They cut only the chemical bonds they want. This could change what we consider recyclable. Chapter 1: Why mixed plastic is so difficult. Plastic is not one single material. PET is used in bottles and polyester fibers. Acrylic materials are used in transparent panels and aquarium tanks. Nylon is found in clothing and industrial products. Polyurethane appears in stretch fabrics, car seats, mattresses, insulation, coatings, and adhesives. Each material reacts differently to heat, pressure, and chemicals. When one type of plastic is collected alone, it may be melted, reshaped, or chemically returned to its original building blocks. But when several plastics are mixed together, recycling becomes far more complicated. A stretchable shirt is a good example. Polyester gives the fabric strength. Polyurethane gives it elasticity. These materials are useful because they are tightly combined. But when the shirt reaches the end of its life, that same combination becomes a major obstacle. It is not realistic to separate every microscopic fiber by hand. So valuable materials may be discarded, not because they have no value, but because we cannot separate them efficiently. The greatest enemy of recycling is not always the waste itself. Sometimes it is the fact that useful materials have become inseparable. Chapter 2: Reversing the old process. Traditional recycling usually begins with separation. First, identify each material, then sort it, then recycle it. The Japanese research team reversed that logic. Instead of perfectly separating the plastics before treatment, they allowed the mixed material to enter the chemical process first. The researchers combined a specially developed iridium catalyst with a potassium base and hydrogen gas. Under these conditions, polyurethane could be chemically broken down, while other polymers, including polyester, acrylic-type PMMA, and nylon, remained undecomposed. The key is selectivity. Polyurethane contains chemical structures known as urethane bonds. The catalyst helps the reaction attack those bonds, while suppressing unwanted reactions in the surrounding materials. Imagine several different ropes tied together. A powerful chemical might burn or cut every rope. This method works more like a pair of molecular scissors. It searches for one particular type of knot and cuts only that knot. The other ropes remain. That is the heart of selective degradation. Chapter 3: What happened to the fabric? The team also tested the process on a blended fiber, containing polyester and polyurethane. After the reaction, the polyurethane was broken down into smaller chemical components, while the polyester remained as a solid fiber. This created two different forms of material. The polyurethane-derived components were in the liquid phase. The polyester remained as an insoluble fiber. Because one was liquid and the other was solid, they could be separated through a relatively simple filtration process. This is important. The polyurethane was not merely destroyed and turned into useless waste. It was broken down toward its original chemical building blocks, which may potentially be used again as raw materials. At the same time, the polyester fiber could be recovered without being chemically decomposed. One difficult waste product could therefore become two separate resource streams. One material remains intact. The other is recovered through chemistry. This is not simply a method for making waste smaller. It is a method for giving each material a different exit. Chapter 4: Where could this technology be used? Polyurethane is almost everywhere. It gives comfort to car seats and mattresses. It helps clothing stretch. It insulates buildings. It is used in foams, coatings, sealants, and adhesives. Many of these products are difficult to recycle because polyurethane is attached to fabric, metal, or other plastics. If selective chemistry can remove one material without destroying the others, future recycling facilities may be able to process complex waste in stages. First, remove polyurethane. Next, recover another polymer. Then separate metals, fibers, fillers, or other valuable materials. waste treatment could begin to resemble a molecular sorting factory. Instead of asking, can workers separate this product by hand? We may begin asking, can chemistry give every material its own exit? That would be a major shift. Complex products would no longer be treated as one useless object. They could be treated as collections of valuable materials, waiting to be recovered. Chapter 5: The Limits. However, this technology is not yet a complete solution to the plastic waste crisis. A successful laboratory experiment does not automatically become an affordable industrial system. Several major questions remain. How quickly can large amounts of waste be processed? How much hydrogen and energy will be required? Can the catalyst be collected and reused many times? Will the process still work when the waste contains dirt, dyes, coatings, flame retardants, or other additives? Will the recovered materials have enough quality to become new products? And most importantly, can the entire process compete economically with producing new plastic? Real waste is messy. Laboratory samples are controlled. Factories must deal with countless combinations of materials and contamination. So it would be premature to say that Japan has solved the plastic problem. But the achievement is still important. It challenges one of recycling's oldest assumptions. Until now, chemical recycling often required the target plastic to be separated before the chemical process could begin. This research suggests that chemistry itself may perform part of that separation. The waste may not need to be perfectly sorted first. Conclusion: the Japanese research team did not create a chemical hammer that smashes every plastic. They created something closer to molecular scissors. Scissors that can enter a mixed material, find polyurethane, cut its bonds, and leave other polymers behind. Some waste is not worthless. It is simply locked inside a structure we have not yet learned how to open. Selective degradation may become one of those keys. If this technology reaches industrial scale, mixed plastic could change from waste that cannot be sorted into a collection of resources, waiting to be recovered. The real breakthrough is not only the ability to destroy one plastic, it is the ability to choose what should be broken down and what should be saved. What do you think matters more for the future of recycling? Better sorting before waste is collected, or better science that can separate materials after they have already been mixed? Share your view in the comments, turning the unknown into hope. This is Hope Reactor.